Welcome to our series on essential concepts and terminology in transportation planning. In this lecture, we will explore the fundamental concept of the Logit model estimation. To estimate a model that most realistically represents travelers' mode choice behavior, we perform the Logit model estimation process. This process is a statistical search procedure aimed at identifying the model with the highest predictive performance. During this process, analysts build various alternative utility functions and evaluate the significance of coefficients and the overall goodness of fit based on statistical testing criteria. The Logit model is a discrete choice model in which the dependent variable takes a value of either 0 or 1 depending on whether a particular alternative is chosen. Therefore, it requires a different estimation method from the ordinary least squares method used in regression analysis for continuous variables. Instead, the Logit model estimates coefficient values using maximum likelihood estimation. MLE is a method that determines the coefficients of the utility function such that the choice probabilities calculated by the model achieve a state that most likely matches the actual observed choice outcomes of individual travelers. In essence, the core objective is to find the set of coefficient values that maximizes the value of the likelihood function. Accordingly, to statistically validate the coefficients estimated by MLE, it is essential to first understand the concept of the likelihood function. The likelihood function represents the joint probability, the probability that the actual choices made by all travelers in the sample occur simultaneously. Mathematically, as shown in the formula on the screen, it is expressed as the product of the individual choice probabilities for every person in the sample. As the total probability of this likelihood function increases, it indicates that the estimated coefficients explain real-world choice patterns more effectively. In practical applications, for computational convenience and clearer interpretation, the log likelihood function, obtained by taking the natural logarithm of the likelihood function, is used instead. Taking the logarithm transforms the multiplication equation into an addition equation, making optimization calculations much easier. Furthermore, it expands small differences in probabilities between 0 and 1 into a broader range in the negative domain, allowing for a clearer identification of the optimal coefficient values. The statistical indicators in the Logit model estimation are interpreted based on these log likelihood values. The theoretical framework and illustrative examples presented here are primarily based on the classic textbook Discrete Choice Analysis by Ben Akiva and Lerman, 1985. The log likelihood function of the Logit model consists of two key components. First, the choice probabilities calculated by the model, and second, an indicator variable that represents an individual traveler's actual choice as either 0 or 1. By applying the natural logarithm to the likelihood function, the complex multiplication formula is transformed into an addition form. As a result, the log likelihood values of individual observations can be independently summed across all travelers. Understanding how the log likelihood value changes within the formula gives an intuitive grasp of its function. If the model assigns a high probability to the alternative that a traveler actually selected, the corresponding log likelihood value will be a negative number close to 0, meaning its absolute value becomes very small. Conversely, if the model predicts a very low probability for the alternative that was actually chosen, the log likelihood value will move deeper into the negative domain, meaning its absolute value becomes extremely large. In conclusion, as the total sum of the log likelihood function across all travelers approaches 0, it indicates that the model describes real-world choice behavior more effectively. To evaluate the performance of the Logit model, three reference log likelihood measures are commonly used: LL0, LLC, and LL beta. First, LL0 represents the case where there is no information available, assuming that the choice probabilities for all alternatives are equal. This corresponds to the lowest level of prediction, where travelers make purely random choices. Therefore, it yields the largest absolute value, meaning the most negative value among the three measures. Second, LLC corresponds to the case where only alternative specific constants are included without any other explanatory variables. This predicts choice behavior based solely on the actual market share information of each mode. Since it reflects more advanced information compared to a random choice, the absolute value of LLC decreases compared to that of LL0. Third, LL beta represents the log likelihood value obtained when all the optimal coefficients that maximize the likelihood function are applied. This value is achieved under the assumption that travelers maximize their utility by comprehensively considering explanatory variables, such as level of service, like travel time and cost, socioeconomic factors, and trip characteristics. Therefore, LL beta represents the maximum possible value that best describes reality, meaning it is the closest to zero. Since individual probabilities are always less than 1, the log likelihood value is always negative. Mathematically, the log likelihood function of a Logit model takes the form of a strictly concave function. This geometric property numerically implies the existence of a single global maximum, mathematically guaranteeing that the coefficients found through maximum likelihood estimation are unique. This property, namely that the same dataset and model structure always produce a stable and unique solution, provides the foundation for treating the Logit model's statistical indicators as reliable and well-defined reference measures. The optimized log likelihood value, LL of beta, allows us to objectively quantify how well the model explains actual traveler choice behavior by comparing it with the baseline measures LL of 0 and LL of C. A representative indicator derived from these comparisons is the likelihood ratio index, commonly referred to as Rho-squared. The Rho-squared index represents the proportion of improvement in model explanatory power from LL of 0, the baseline of no information, to LL of beta, the optimized log likelihood value. Additionally, the Rho-squared with respect to constants, which uses LL of C as its baseline, can also be utilized for model evaluation. This index measures the net increase in explanatory power contributed purely by the explanatory variables relative to the existing market share information rather than a random choice. Consequently, although its value typically appears somewhat lower than the standard Rho-squared, it holds significant analytical value in identifying the pure contribution of the explanatory variables. However, similar to the coefficient of determination, R-squared, in ordinary regression analysis, the Rho-squared index in a Logit model tends to increase as additional explanatory variables are introduced into the model. Therefore, to evaluate both the simplicity and economy of the model, it is necessary to account for the number of explanatory variables, or the degrees of freedom. The statistic that adjusts for this is the adjusted Rho-squared. It is important to note that the Rho-squared index in a Logit model has a different scale and meaning from the R-squared in regression analysis. Consequently, the practical criteria for judgment are also applied differently. In practice, a Rho-squared value between 0.2 and 0.4 is generally considered to indicate an excellent and reliable model with good explanatory power. The fact that the difference in log likelihood values between two models follows a chi-square distribution provides an objective and scientifically rigorous basis for evaluating the reliability of Logit models. This statistical method, which evaluates model fit using the difference between log likelihood values, is called the likelihood ratio test. Because of the mathematical properties of logarithms, the difference between two log likelihood values corresponds to the logarithm of the ratio of the two original likelihood values. In practice, three main types of likelihood ratio tests are commonly used. The first type is -2 times LL of 0 minus LL of beta, which tests the overall significance of the model. This statistic tests the null hypothesis that all coefficients in the utility function are equal to 0. In other words, it determines whether the developed model is statistically superior to a model representing purely random choice with no information. This statistic follows a chi-squared distribution, and its degrees of freedom are equal to k, which is the number of estimated coefficients in the utility function. If the calculated likelihood ratio value exceeds the critical chi-square value for a given significance level and k degrees of freedom, we can conclude that the model is statistically significant as a whole. The second type is -2 times LL of C minus LL of beta, which tests the significance of the explanatory variables. This tests the hypothesis that all coefficients except for the alternative specific constants are 0. The degrees of freedom for this test is k minus n, where k is the total number of coefficients and n is the number of alternative specific constants. This test measures how much more effectively the newly introduced explanatory variables explain choice behavior compared to when only the existing market share information is available. In a logically well-specified model, both of these first two tests usually reject the null hypothesis. Therefore, in practice, they may offer relatively low distinctiveness when refining models. Consequently, the third type, -2 times LL of beta R minus LL of beta U, is the most critical tool in practical model development. Here, LL of beta R represents the log likelihood of a restricted model, where certain constraints are applied, such as excluding specific variables or setting coefficients to be equal. LL of beta U represents the log likelihood of an unrestricted model, where all parameters are freely estimated. The null hypothesis for this test is that the restricted model is the true model, meaning that adding new variables or relaxing constraints does not contribute to improving the model. If the calculated likelihood ratio statistic is larger than the critical value, the unrestricted model is considered statistically superior and is therefore selected. Conversely, if it is smaller than the critical value, it is more rational to maintain the simpler restricted model, keeping in mind the simplicity and economy of the model. In conclusion, the estimation process of the Logit model can be defined as an iterative procedure of performing these likelihood ratio tests to identify the optimal combination of explanatory variables and utility function structure, balancing both statistical significance and behavioral realism. To develop a Logit model with reliable predictive performance, the analysts should systematically examine the following 6 key checklist items. First, perform statistical significance testing. The Rho-squared index provides an overall measure of explanatory power, while the likelihood ratio test evaluates the statistical significance of the model as a whole. In addition, the t-statistics should be carefully examined to determine whether individual explanatory variables are statistically significant at acceptable confidence levels. Second, verify the signs of the coefficients and their behavioral validity. Checking the sign of a coefficient is a fundamental intuitive step and should be considered even before statistical significance. For example, coefficients associated with travel time and travel cost must be negative. If a coefficient is estimated with a sign that contradicts behavioral common sense, this may indicate input data errors or a fundamental model misspecification. Third, examine the relative magnitudes of the estimated coefficients. In a Logit model, the estimated coefficients are combined with the scale parameter mu, which is related to the variance of the random error term. Therefore, rather than interpreting the absolute values of individual coefficients, we must examine the ratios between variables to understand their substitution effects. A representative example is the value of time, calculated by dividing the travel time coefficient by the travel cost coefficient. It is essential to verify whether these proportional values fall within the range of social norms or prior research to ensure that the relative magnitudes of the coefficients are reasonable. Fourth, evaluate the magnitudes of the alternative specific constants. Constants capture inherent preferences for each alternative that are not explained by the explanatory variables included in the model. If a constant term for a particular alternative is excessively large, this may suggest that important explanatory variables influencing choice behavior have been omitted from the model. Fifth, examine the IIA property and independence among alternatives. We must verify whether the IID, independent and identically distributed assumption of the error terms, the fundamental premise of the Logit model, holds true. If excessive correlation exists among certain alternatives, we should consider removing that correlation by specifying common attributes as variables or transitioning to an extended model, such as the nested Logit model. Sixth, assess market share reproduction and policy sensitivity. The aggregate predicted choice probabilities should closely reproduce the actually observed market shares. Furthermore, we must validate the model's practical suitability through elasticity analysis, ensuring that choice probabilities fluctuate within a reasonable range when policy scenarios such as fare increases or travel time reductions are applied. To illustrate the process of selecting the statistically superior model among alternative specifications, consider a practical example. We are comparing and evaluating two different models in a scenario with three mode choices: private automobile, bus, and metro rail. Model 1 serves as our baseline model, which includes travel time, T, and the cost-to-income ratio, CTI, as its explanatory variables. There are two primary reasons why the cost variable is specified as a ratio to income rather than simply as a standalone cost. First, it reflects the reality that the economic sensitivity individual travelers feel varies according to their income levels. Second, it helps mitigate multicollinearity, a problem where a high correlation between travel time and travel cost might cause the estimated coefficients to have irrational positive signs. Next, to enhance the explanatory power of the model, we established a new hypothesis. Regularly repeated daily commuting trips will exhibit different mode choice behaviors compared to other trip purposes. Based on this hypothesis, we built Model 2 by adding a dummy variable, TP, which indicates whether the trip purpose is commuting, to the baseline Model 1. Now, we will perform a statistical test to determine which of these two models is superior: Model 1, our baseline specification, or Model 2, which has been extended by adding the new explanatory variable. To compare the goodness of fit of the two models, we can first utilize the adjusted Rho-squared index. The reason for comparing the adjusted Rho-squared rather than the standard Rho-squared is that the two models have a different number of explanatory variables. The standard Rho-squared has a mathematical property that always increases whenever additional variables are introduced. Therefore, it is rational to make a fair comparison using a measure adjusted for the degrees of freedom based on the number of variables. If the adjusted Rho-squared of Model 2 is greater than that of Model 1, we can initially judge that Model 2 is statistically superior. For more rigorous statistical evidence, a likelihood ratio test can be performed. In this context, Model 1 serves as the restricted model, where the coefficient of the added variable is constrained to 0, while Model 2 is the unrestricted model, where all coefficients are freely estimated. Since exactly one variable is added to Model 2, the degrees of freedom for this test equal 1. The calculated likelihood ratio test statistic is compared to the critical chi-square value at a specific confidence level such as 95%. If the calculated test statistic exceeds the critical value, it indicates that the added variable made a statistically significant contribution. Therefore, we reject the null hypothesis and finally adopt the unrestricted Model 2. This implies that the probability of achieving this level of model improvement purely by chance, even though the restricted model was the true model, is less than the 5% significance level, making it extremely rare. Since such an exceptional event is highly unlikely to be observed under normal circumstances, we conclude that Model 2 is statistically superior. Conversely, if the calculated likelihood ratio test statistic is less than the critical value, it means that the improvement in explanatory power is minor despite adding the variable. In this case, considering the simplicity and economy of the model, it is statistically more valid to retain the simpler Model 1. This likelihood ratio testing process can be widely applied beyond just adding or deleting a single variable. It is an objective method for identifying the optimal utility structure among nested alternative models to best represent actual traveler choice behavior. Another effective way to enhance the explanatory power of our baseline Model 1 is to change the specification format of the explanatory variables. Specifically, this process statistically tests whether a specific variable should be treated as a generic variable, assuming it has the exact same impact across all modes, or as an alternative specific variable, assuming its influence varies by mode and thus requires separate independent coefficients. In Model 1, the coefficient beta 2 for the cost-to-income ratio, CTI, was assumed to be identical across all modes. In contrast, Model 3 introduces the hypothesis that users of private automobiles, buses, and metro rail may exhibit different sensitivities to cost. Accordingly, Model 3 is structured so that each mode has its own unique cost coefficient, aiming to mathematically capture the differences in the perceived financial burden felt by travelers. Now, we compare and evaluate the goodness of fit of Models 1 and 3 using the likelihood ratio test. In this context, Model 1 serves as the restricted model, constrained by the assumption that all cost coefficients are equal, while Model 3 is the unrestricted model, where each mode's coefficient is freely estimated. While Model 3 can describe traveler behavior more flexibly, it requires estimating two additional parameters. Therefore, this analysis essentially tests whether the improvement in explanatory power is sufficient to justify the addition of two more coefficients. The calculated likelihood ratio test statistic is compared against the critical chi-square value with 2 degrees of freedom, as shown on the screen. If the calculated test statistic exceeds the critical value, the hypothesis that cost sensitivity differs across modes is statistically supported. Consequently, we reject the null hypothesis and adopt Model 3. This implies that if the restricted Model 1 were the true model, the probability of observing such a significant improvement purely by chance is extremely low. Thus, we confirm the statistical superiority of Model 3 based on robust empirical evidence. Conversely, if the calculated statistic is smaller than the critical value, it implies that the differences in sensitivity across modes are statistically negligible. In that case, it is more rational to retain the simpler Model 1 based on the principle of model simplicity and economy. Evaluating alternative variable specifications in this manner is an effective step in developing more refined behavioral models. In particular, choosing between generic and alternative specific variables is a way to appropriately represent the underlying psychology of travelers' mode choice behavior. Although the nonlinear effects of explanatory variables on utility can be captured using logarithmic or exponential functions, they can also be effectively represented through the line segmentation, which specifies different sensitivities for different travel time intervals. For example, this reflects the realistic behavioral assumption that the perceived resistance of a 5-minute change for a short 20-minute trip differs from that of a 5-minute change for a long-distance trip exceeding an hour. Line segmentation specification estimates different slopes for each travel time interval, allowing for a direct comparison of traveler sensitivity across different time ranges. While Model 1 applied a single coefficient to all travel times, our alternative specification, Model 4, divides travel time into 3 distinct intervals: under 20 minutes, between 20 and 50 minutes, and over 50 minutes. We then define 3 new travel time variables, TS1, TS2, and TS3, to independently estimate the sensitivity for each interval. As shown in the variable construction formulas on the screen, the line segmentation specification ensures that the segments are connected linearly so that the overall utility function remains continuous. For instance, if the actual travel time is 35 minutes, 20 minutes are assigned to the first segment variable, TS1, 15 minutes to the second segment variable, TS2, and 0 to the third segment variable, TS3. In another example, for a 55-minute trip, 20 minutes are assigned to TS1, 30 minutes to TS2, and the remaining 5 minutes to TS3. By decomposing the overall travel time variable into 3 consecutive intervals in this manner, the overall utility function remains continuous without any breaks, while allowing for different slopes, that is, distinct coefficient values across the different intervals. Based on this hypothesis, we perform a likelihood ratio test to compare the goodness of fit of Model 1 and Model 4. Here, Model 1 serves as the restricted model, constrained by the assumption that the coefficients for all travel time intervals are identical, while Model 4 is the unrestricted model, which allows each interval-specific coefficient to be estimated independently. Since the number of travel time coefficients increases from 1 to 3, the degrees of freedom for this likelihood ratio test is 2, as shown on the screen. If the calculated statistic exceeds the critical chi-square value with 2 degrees of freedom, the hypothesis that travel time sensitivity differs across intervals is statistically supported. Consequently, we reject the null hypothesis and adopt Model 4. This implies that if the restricted Model 1 were the true model, the probability of observing such a significant improvement in model fit purely by chance is extremely low. Thus, we confirm the statistical superiority of Model 4 based on robust empirical evidence. Conversely, if the calculated statistic is smaller than the critical value, it implies that the improvement in explanatory power from segmenting the intervals is negligible. In that case, it is more rational to retain Model 1 based on the principle of model simplicity and economy. Admittedly, the line segmentation specification has a practical limitation in that the breakpoints, such as the 20-minute and 50-minute thresholds in this example, rely on the analyst's subjective judgment. Nevertheless, as shown in the graph on the left, it possesses a practical advantage. It can flexibly describe changes in traveler sensitivity based on actual observed data. In particular, these analytical results provide policymakers with a scientific and empirical foundation to understand why sharp fluctuations in transportation demand may occur within specific travel time ranges. Model 1 is the base model estimated using the entire dataset pooled together. This specification assumes that all travelers have the exact same sensitivity to explanatory variables, such as travel time and travel cost, regardless of their socioeconomic attributes like gender or age. In reality, however, mode choice behaviors and preferences may vary significantly across different traveler groups. Therefore, it is necessary to examine whether the explanatory and predictive power of the model can be improved through market segmentation, which separates models by groups with distinct characteristics. As an example, we compare the pooled Model 1 with Model 5, which is expanded by segmenting the data into 2 separate specifications, a male group model, Model 5-1, and a female group model, Model 5-2. In this context, the fully integrated Model 1 serves as the restricted model because it imposes the strict constraint that the behavioral parameters for both males and females are identical. In contrast, Model 5 is the unrestricted model because the coefficients for each gender group are estimated independently without any equality constraints. Given the 3 choice alternatives and the utility structure shown on the screen, Model 1 requires a total of 8 parameters to be estimated. On the other hand, Model 5 requires a total of 16 parameters, 8 for the male group and 8 for the female group. Therefore, the difference in the number of estimated parameters between the 2 models, which is 8, becomes the degrees of freedom for this likelihood ratio test. The log likelihood of the unrestricted Model 5 is the sum of the log likelihood values from the male and female models. If the calculated likelihood ratio test statistic using the log likelihood values of Model 1 and Model 5 exceeds the critical chi-square value with 8 degrees of freedom, we reject the null hypothesis that male and female choice behaviors are identical. Consequently, we conclude that the market segmentation model is statistically superior. This implies that if the restricted Model 1 were the true model, the probability of observing such a significant improvement in model fit purely by chance is extremely low. Thus, we confirm the statistical superiority of the segmented Model 5 based on robust empirical evidence. Conversely, if the calculated test statistic is smaller than the critical value, it is statistically more rational to retain the simpler pooled Model 1 rather than complicatedly dividing the sample into separate groups, based on the principle of model simplicity and economy. An important additional diagnostic step is to compare the magnitudes of the estimated parameters between the male and female models. If all parameters in the male model are larger or smaller than those in the female model by a constant proportion, it suggests that their fundamental behavior is not different. Rather, it indicates that scale parameter mu of the distribution of the random error terms, which is inversely related to the variance, differs between the two groups. However, if the proportional changes vary across different parameters, it indicates a fundamental difference in the underlying choice behaviors and tastes between genders. Furthermore, hypothesis testing can be conducted at the level of individual variables, not just for the overall model. To test the null hypothesis that there is no difference in a specific parameters between the two groups, we can calculate and evaluate a t-statistic using the estimated parameters and their standard errors. Through this approach, we can empirically verify specific hypotheses such as, are females statistically more sensitive to travel cost than males? In addition to validating improvements in the model's predictive power, this market segmentation process provides a critical, scientific, and logical foundation for understanding the distinct characteristics of different demographic groups, thereby enabling the design of customized transportation policies. To correctly interpret Logit model estimation results, it is absolutely essential to understand the scale parameter mu. Let us examine why this scale parameter is inevitably required in the model estimation process. The empirical survey data we collect inherently contains substantial uncertainty, including diverse individual preferences and unobserved behavioral variations. Statistically, this uncertainty is represented by the variance of the random error term, reflecting the volatility of the data. However, for mathematical and computational convenience, the Logit model estimation algorithm assumes that the error terms follow a standard Gumbel distribution, which has a fixed variance. Consequently, a discrepancy arises between the true magnitude of uncertainty in the real-world data and the fixed numerical scale of the assumed standard Gumbel distribution. To reconcile this discrepancy, a mediator is required to proportionately expand or contract the magnitude of the utility function so that the empirical variance aligns with the assumed distributional variance. This mediator is precisely the scale parameter mu. For this reason, the estimated coefficients provided by statistical software packages are not purely the intrinsic behavioral values. As shown in the box on the bottom right of the screen, the estimated coefficient is output as the product of the true behavioral coefficient and the scale parameter mu. Consequently, we must recognize that the absolute magnitude of the estimated coefficients we obtain does not represent pure behavioral sensitivity alone, rather it varies depending on the variance of the error term embedded within that specific dataset. As explained at the bottom of the screen, the scale parameter mu is inversely related to the standard deviation and variance of the distribution of the random error terms. That is, as the data uncertainty increases and the error variance grows, the scale parameter mu decreases, resulting in smaller estimated coefficients. For this reason, rather than interpreting the absolute values of individual coefficients, it is statistically valid to interpret them as relative ratios between variables, from which the influence of error variance has been completely eliminated. A representative example is the calculation of the value of time discussed earlier. Because the travel time coefficient and the travel cost coefficient are multiplied by the exact same scale parameter mu, taking the ratio of the two coefficients mathematically cancels out mu, leaving only the pure behavioral trade-off ratio. This concept of the scale parameter is critically utilized in practical analysis when combining revealed preference data, RP data, and stated preference data, SP data. SP data, which evaluate hypothetical scenarios, inherently possess a different level of response uncertainty, meaning error variance, compared to RP data, which reflect actual observed behavior. Therefore, when integrating both datasets into a single pooled estimation framework, a scaling procedure must precede the estimation to adjust the ratio of the scale parameters and align the data onto the same baseline. Furthermore, this concept is essentially applied when constructing a nested Logit model with a hierarchical structure to overcome the limitations of the IIA property. This is because the random error variances differ between the upper level and the lower level nests. Logically, the error variance of the upper structure is larger than that of the lower structure, which consists of highly similar alternatives. Due to the inverse relationship, the magnitude of the scale parameter for the lower nest must be larger than that of the upper. To satisfy this condition of upward consistency, the ratio of the scale parameters between the two levels must fall strictly between 0 and 1. If this condition is violated, it implies that the specified nested structure does not conform to the actual choice behavior of travelers or the error structure of the data. In such cases, the analyst should reevaluate and test alternative nesting combinations to find a structure that fits the data. If a proper scale parameter ratio cannot be obtained, or if the value converges to 1 despite various combinations, it is a practically rational decision to retain the simpler and more stable multinomial Logit model rather than forcing an overly complex structure based on the principle of model simplicity and economy. In conclusion, analysts must clearly recognize the embedded presence of the scale parameter within estimated Logit coefficients. It requires the insight to interpret estimation results from the perspective of relative ratios, where the influence of the scale parameter is neutralized rather than focusing on the superficial absolute magnitudes of the coefficients. Estimating a sophisticated Logit model requires an enormous amount of time and cost, ranging from data collection and cleaning to iterative statistical testing of alternative variable specifications. In practice, however, analysts frequently encounter situations where rapid analysis results are required for swift policy decisions. In such situations, elasticity analysis and the incremental Logit model provide highly efficient and valuable analytical alternatives. In the context of a Logit model, elasticity measures the percentage change in a mode's choice probability resulting from a 1% change in a particular explanatory variable. As shown in the formulas on the screen, these measures are classified into direct elasticity, which represents the change in a mode's probability due to a change in its own attribute, and cross elasticity, which captures the impact of changes in competing modes' attributes. Furthermore, it is possible to estimate utility function coefficients beta k relatively easily by back-calculating from these elasticity formulas, particularly the direct elasticity formula. If we have prior knowledge of the current market shares, Pi, the variable values, xki, and the typical elasticity indicators commonly accepted in the market, we can rapidly derive approximate coefficient values without the need for full-scale model estimation. However, an important point to note in this interpretation is the fact that the scale parameter, mu, is inherently embedded within the estimated coefficient beta k. Therefore, we must maintain the insight that a smaller variance of the distribution of the random error terms, meaning less data uncertainty, leads to a larger scale parameter mu, which in turn produces greater sensitivity in the resulting elasticity responses. Applying these back-calculated or predefined coefficients to the incremental Logit model, also widely known as the pivot point model, allows for a quick estimation of changes in mode shares due to environmental shifts without the need for a complex full-scale model estimation process. The primary advantage of the incremental Logit model, as shown in the general formula on the screen, is that it predicts future market shares by considering solely the changes in the explanatory variables, delta x, directly using the currently observed market share as the anchor or baseline. This mathematical structure implicitly assumes that the currently observed market shares already inherently embody the potential impacts of omitted variables, alternative specific constants, and other factors not explicitly represented in the model specification. Therefore, when forecasting the impacts of short-term transportation policy changes, this model not only ensures remarkable analysis speed, but also provides practical realism, since it accumulates changes directly onto observed market conditions rather than relying solely on theoretical equilibrium outcomes. In summary, elasticity analysis and the incremental Logit model serve as highly practical methodologies. Without requiring large-scale new data collection, they enable analysts to rapidly derive insights using only existing statistical indicators and mathematical relationships, thereby providing policymakers with scientifically grounded, timely strategic insights. In the next lecture of our series on essential concepts and terminology in transportation planning, we will focus on the topic of the traffic assignment.
Thank you for watching. I would love to hear your thoughts or comments on today's lecture. If this explanation was helpful, please like and subscribe to support this series.